I'm Adam from RFOXiA, from our real lab. Today we're answering a question that has cost developers more hours than almost anything else in embedded hardware. Why does a firmware flash fail when the code is correct? Let me start with what actually happens during a firmware flash, because most developers treat it as a black box, and that is the first mistake. When your ST-Link programmer initiates a flash sequence, it establishes a debug interface with your target microcontroller, typically over SWD, serial wire debug. The programmer sends a reset, halts the core, erases the target flash sectors, and then begins writing firmware in blocks. Each write operation is verified. If the verification fails, the programmer either retries or aborts depending on its configuration. That entire sequence, halt, erase, write, verify, depends on the target device being in a known stable electrical state from the first clock cycle to the last. Here is where the problem begins. Every one of those operations draws current, not a constant current, a variable pulsed current that changes as the internal flash write circuitry cycles. On an STM32 class microcontroller, for example, the flash programming current can spike 2 to 4 times higher than idle draw in microseconds. That is not a slow event. It happens faster than most power supplies can respond. Now consider where most developers get their power. A laptop USB port, a phone charger, a bench supply that was designed for audio equipment and repurposed because it was available. These sources were not designed for this load profile. When the current demand spikes, the voltage drops, the microcontroller's VDD rail sags. If it sags far enough, even briefly, the flash write circuitry may complete a partial write and then receive corrupted data, or the core may experience a brownout reset mid-operation. The result is not always obvious. Sometimes you get a clean error from the programmer and you know something failed. More often the flash partially completes, the device boots, it behaves strangely, it crashes at runtime under load, it works in your lab and fails in the field. You spend 4 hours in the debugger convinced the firmware has a logic error. It does not. The firmware was written incorrectly because the power supply could not hold the rail. This is not a hypothetical failure mode. This is one of the most common root causes of inexplicable embedded development problems, and it is almost never the first thing anyone checks. The reason it is hard to diagnose is that the failure is invisible at the level most developers operate. You are looking at code, you are looking at register values in the debugger. You are not looking at the voltage rail in real time with an oscilloscope during the flash operation. If you were, you would see it immediately, a sag, a ripple, a transient spike when the flash controller transitions between erase and write states. The physics is not subtle. The instrumentation required to see it is just not part of the average debugging workflow. Let me explain the specific mechanisms, because there are several and they interact. Voltage sag is the most direct. USB hosts are specified to supply 5 volts at 500 milliamps for USB 2.0, or up to 900 milliamps for USB 3.0. In practice, the actual voltage delivered depends on cable resistance, the quality of the host controller, and what else is drawing current from the same bus. A 2-meter USB cable with 0.5 ohm resistance drops 250 millivolts at 500 milliamps of draw. Before your programmer has done anything, you may already be operating with a reduced supply margin. Add the current spike from flash programming and you are now exploring the lower boundary of your microcontroller's operating voltage specification. Ground noise is the second mechanism. When multiple devices share a USB ground rail, your programmer, your target board, your logic analyzer, your laptop chassis ground, you create conditions for ground loops. A ground loop means that what you think is 0 volts at the programmer is not actually 0 volts relative to the target device's ground reference. A difference of 50 to 100 millivolts in the ground reference can be enough to cause SWD communication errors. The programmer interprets this as a protocol failure, reports a generic flash error, and you go looking for the wrong thing. Power supply ripple is the third mechanism and arguably the most insidious. Cheap switch mode power supplies, which describes most phone chargers and low-cost bench supplies, produce a regulated average voltage, but that voltage has ripple on it. Ripple is a periodic oscillation of the output voltage at the switching frequency, typically 50 to 200 kHz. The amplitude of the ripple depends on the quality of the output filter capacitors. On a cheap supply, ripple can be 50 to 100 millivolts peak to peak. Your microcontroller's flash write voltage thresholds have margins measured in tens of millivolts. The intersection of those two facts is not a comfortable place to run a firmware flash. The conventional advice at this point is to add decoupling capacitors close to the target device's power pins. This is correct and you should do it. But decoupling capacitors address high-frequency noise at the board level. They do not address the upstream problem of a power source that cannot maintain stable voltage under variable load. You are treating a symptom. The actual fix is a power source that was designed to deliver stable, clean voltage under precisely the kind of variable pulsed load that firmware programming creates. That means a source with low output impedance across the relevant frequency range, sufficient current reserve to absorb transient spikes without drooping, and electrical. That is the physics of why an unstable power source corrupts a firmware flash, not randomly, not rarely, but predictably and silently. Now let me show you the hardware that eliminates this problem. This is the supercapacitor battery system. 1100 farads, storing 8800 joules. The reason this matters for firmware development is output impedance. A supercapacitor delivers charge almost instantaneously under transient load. When the flash controller spikes its current demand, the rail does not sag. There is no voltage droop, no ripple from a switching regulator, just stable voltage held exactly where it needs to be for the entire duration of the flash operation. This is the 12 volt 5 amp charging adapter. It charges the supercapacitor bank through a 4 volt 10 amp input stage, meaning the full 1100 farad bank reaches capacity in under 5 minutes. In practice, that means you charge once in the morning and the power system is ready for a full day of development. There is no waiting for a battery to cycle, no degradation after 1,000 charge cycles. The supercapacitor technology does not age the way lithium chemistry does. This is the complete module stack running on a single charge, BLE module, GNSS module, sensors module, all drawing from the same power bank simultaneously for a full working day. When you are doing firmware development in the field or in a lab without a reliable bench supply, this matters. Your programming environment, your target device, and your sensor stack all share the same clean, stable voltage source. There is no mixed ground problem when everything is on the same isolated rail. This is the integrated ST-Link programmer. It connects directly to the Multinav Pro Plus BLE module through the flat ribbon interface. No adapters, no improvised wiring, no opportunity for a loose connection to introduce resistance into the SWD line. The programmer draws its power from the same supercapacitor bank as the target device. Ground reference for the programmer and target are identical. This eliminates the ground loop failure mode entirely before the first flash command is issued. This is the complete connectivity kit, flat ribbon cables that handle both power delivery and SWD signal routing between the module stack and the programmer. Flat ribbon construction minimizes inductance on the SWD data lines, which reduces signal integrity problems at higher clock rates. Everything you need to go from unboxing to first successful firmware flash is in this kit. No sourcing individual cables, no improvising. The connection is defined, repeatable, and correct every time. A development laptop. This is the engineering case for a dedicated power system for development work. Not because it is convenient, though it is, but because the alternative is building your development workflow on a foundation that will occasionally, unpredictably, silently corrupt your firmware and cost you hours finding a fault that was never in your code. The Multinav Pro Plus Power Program Kit gives your ST-Link programmer the clean, stable power it needs so that every firmware flash works the first time every time.